Imagine a universe woven with an invisible thread, a cosmic adhesive binding galaxies, stars, and ultimately our very existence. This isn't science fiction, but a profound possibility explored by physicists. What if dark matter is the fundamental glue holding everything together? For decades, scientists have grappled with a perplexing cosmic mystery. The visible matter we observe, all the stars, planets, and gas, simply doesn't account for the gravitational forces at play in the universe. Something else must be providing the necessary scaffolding. This invisible influence, which we've dubbed dark matter, doesn't emit, absorb, or reflect light, making it incredibly difficult to detect directly. Its presence is inferred through its gravitational effects on visible matter. Early observations of galaxy rotation curves provided the first compelling evidence. Galaxies spin much faster at their outer edges than expected, implying a massive, unseen halo of matter extending far beyond their visible boundaries. Fritz Zwicky, a Swiss astronomer, first coined the term dark matter in the 1930s after studying the Coma cluster of galaxies. He noticed the galaxies were moving too fast to remain gravitationally bound by their visible mass alone. His calculations suggested that a significant portion of the cluster's mass was missing, leading to the groundbreaking, albeit initially dismissed, hypothesis of an invisible component. Vera Rubin and Kent Ford's work in the 1970s on detailed galaxy rotation curves further solidified the case. Their precise measurements showed that nearly all spiral galaxies exhibited this anomalous behavior. Without dark matter, galaxies would simply fly apart, unable to maintain their intricate structures. Dark matter acts as a gravitational scaffold, preventing the cosmic ballet from unraveling. The reigning cosmological model, lambda CDM, posits that dark matter makes up about 27% of the universe's total mass energy content. This dwarfs the mere 5% attributed to ordinary baryonic matter. If dark matter indeed is this pervasive, its role extends far beyond merely holding galaxies together. It could be the foundational ingredient for the formation of the large-scale structures we observe. In the very early universe, after the Big Bang, ordinary matter was too hot and energetic to clump together effectively due to radiation pressure. Dark matter, however, was unaffected by this force. This allowed dark matter to begin forming gravitational wells, attracting and accumulating around nascent overdensities. These dark matter halos served as cosmic cradles for the birth of stars and galaxies. Without these pre-existing dark matter structures to provide the initial gravitational pull, ordinary matter would have struggled to collapse and form the complex cosmic tapestry we see today. Essentially, dark matter acted as the gravitational framework, allowing ordinary matter to fall into its potential wells and condense into galaxies, galaxy clusters, and even superclusters. This elegant mechanism explains why galaxies aren't randomly scattered throughout the universe, but are instead arranged in a vast, interconnected network like a cosmic sponge. Another fascinating implication is the role of dark matter in galaxy collisions and mergers, commonplace events in the universe's history. During galaxy collisions, the visible gas and dust often interact violently, forming shockwaves and new stars. Dark matter, however, passes through itself almost unimpeded. This separation of dark and ordinary matter during mergers provides crucial evidence for dark matter's existence and its non-interacting nature. The most famous example is the bullet cluster. In the bullet cluster, the hot gas from the colliding clusters was slowed by drag forces, forming a shockwave. But the dark matter, identified by gravitational lensing, passed right through. This clear separation of the visible matter, the pink gas, and the dark matter, the blue gravitational lensing map, is a powerful, direct proof of dark matter's existence and its ethereal nature. If dark matter didn't exist, or if it behaved like normal matter, the bullet cluster observations would be impossible to explain. It's a cosmic smoking gun. So what exactly is this cosmic glue? Current theories propose that dark matter consists of exotic, weakly interacting massive particles, or WIMPs. These hypothetical particles would interact with ordinary matter only through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Underground laboratories around the world are trying to catch these elusive particles directly. Detectors shielded from cosmic rays hope to observe a rare collision between a WIMP and an atomic nucleus. Experiments like XENONNT and Lux Zeppelin use ultra-pure liquid noble gases, hoping for a tiny scintillation of light or an ionization event when a WIMP strikes an atomic nucleus. Other contenders for dark matter include axions, even lighter and more elusive particles, or sterile neutrinos, heavy counterparts to the known neutrinos. The search remains elusive, with no definitive direct detection yet. This has led some physicists to consider alternative theories, though they face significant challenges. One such alternative is Modified Newtonian Dynamics, or MOND, which proposes that gravity behaves differently on galactic scales than predicted by Einstein's theory of general relativity. MOND suggests that at very low accelerations, typical of the outer regions of galaxies, gravity becomes stronger, eliminating the need for dark matter. While MOND has had success explaining galaxy rotation curves, it struggles to account for phenomena like the bullet cluster or the cosmic microwave background anisotropies. These robust pieces of evidence for dark matter's existence mean that MOND would need radical adjustments to remain viable, making WIMPs and other exotic particles a more favored explanation. If dark matter truly is the glue, how far does its influence extend? Could it be affecting phenomena on much smaller scales, even within our Milky Way galaxy? Astronomers are exploring whether dark matter could subtly influence the orbits of stars within globular clusters or even the distribution of gas clouds. Some theories even propose that dark matter could accumulate in the centers of stars or planets, indirectly affecting their internal dynamics or energy transport. However, such interactions would be incredibly weak, and current observations have not yet provided definitive evidence for dark matter's influence on these smaller, localized scales. The direct detection of a dark matter particle would be a monumental discovery, revolutionizing our understanding of fundamental physics and the universe itself. It would confirm the existence of matter beyond the standard model of particle physics and open up entirely new avenues of research into the nature of reality. Furthermore, if we understood the true nature of dark matter, it could help us refine our models of cosmic evolution, from the Big Bang to the present day. Perhaps there's even an entire dark sector of particles and forces, interacting only with each other and through gravity with our visible universe. This dark sector could have its own rich phenomenology, with its own dark photons or dark electrons, forming a parallel reality that largely remains hidden from us. The possibility of dark matter being the universal glue challenges us to think beyond what we can directly perceive, pushing the boundaries of human knowledge. Consider the implications for cosmology. If dark matter particles have a different temperature or interaction strength, it would drastically alter the formation of structure in the early universe. For instance, hot dark matter fast-moving particles would smooth out small-scale density fluctuations, preventing the formation of small galaxies. Cold dark matter slow-moving allows for more hierarchical structure formation. Current observations largely favor the cold dark matter model, as it best supports the observed distribution of galaxies and galaxy clusters in the cosmic web. However, there are still some small-scale discrepancies, such as the cusp core problem in galaxy centers, where simulations predict denser dark matter halos than observed. These puzzles hint that dark matter might not be uniformly simple, perhaps engaging in subtle, non-gravitational interactions that we haven't yet accounted for. The search for dark matter exemplifies the scientific process, formulating hypotheses, gathering evidence, refining theories, and constantly pushing the frontiers of discovery. From the outer reaches of the universe to the subatomic realm, scientists are relentlessly pursuing this elusive component that constitutes the majority of the cosmos. If dark matter truly is the glue, then understanding its composition and properties is paramount to completing our cosmic narrative and unlocking the universe's deepest secrets. Our current understanding of the universe relies heavily on the existence of dark matter. Remove it, and the cosmic fabric unravels into a vastly different and largely inexplicable story. The implications reach into the very earliest moments of the Big Bang, influencing how the first structures emerged from the primordial soup of particles. Without dark matter's gravitational influence, the initial density fluctuations would have been too small to ever grow into the galaxies and clusters we see today. It's the silent architect, the invisible framework upon which the luminous universe has been built, shaping the very largest structures in astounding detail. The ongoing experiments at CERN and other particle accelerators also play a crucial role, searching for new particles and interactions that could shed light on dark matter's identity. By recreating the extreme energies of the early universe, scientists hope to produce dark matter particles in controlled laboratory settings, a holy grail for particle physics. Space telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, continue to map the universe with unprecedented precision, providing more detailed gravitational lensing observations. These observations offer indirect but powerful ways to see dark matter's distribution, helping to constrain its properties and rule out alternative theories. The pursuit of dark matter is a testament to humanity's insatiable curiosity and our drive to understand the fundamental nature of our existence. Discovering the true nature of dark matter would not just fill a gaping hole in our cosmic understanding, it would unveil a hidden dimension of reality, profoundly changing our perspective. Until then, dark matter remains the universe's most enigmatic secret, the invisible glue holding everything together, waiting for us to finally pull back the curtain and reveal its true identity.